In this video, we'll introduce and discuss several different types of counting rules. As we begin this section, one interesting question that many students have is why do we talk about counting rules in a chapter on probability? So one of the things that we often do when we're calculating especially classic probability is we look at the size of the event space and the size of the sample space. Previously, we found these by writing out the event space or the sample space and counting up the number of elements in each. But what if we didn't have to write out the entire space before counting all of the elements? This is where counting rules comes into play, and it will save lots of time in the future. So there's going to be several different kinds of counting rules. We'll go through examples of each. The first is the fundamental counting rule. So if we have several different events as part of our probability experiment, where the first one has a certain amount of possibilities, we'll just call it K1 for the first event. The second one has a certain amount of possibilities, we'll call it K2, and so on. Then the total number of outcomes that could possibly happen is the number of possibilities in the first event times the number of possibilities in the second event, and so on. This can be used to find the size of the sample space. So a couple common Ks are for a die, we have 6 total options. For a coin, we have 2 total options, etc. So these are some Ks that we can deal with. So for instance, recall when we looked at the sample space of the gender of 3 children. If we're looking at 3 kids, each of the children, so there's 3 events, child 1, child 2, child 3, each of them have 2 possible options. So each of those Ks are going to be 2. 2 options for the first child, 2 for the second, 2 for the third. Boy, girl, boy, girl, boy, girl. So the fundamental counting rule indicates that the total number of possibilities is 2 times 2 times 2. It is 8. So this wasn't too hard to do by hand. I mean, we did it at the beginning of this chapter. But imagine if you had to do this for 10 children. If you had to write that out, recall the tree that we made when we made these 8. Think about if you had to do this for 10 kids. Now, if you're doing it for 10 kids, this would be 2 times 2 times 2 for each of the 10 kids. So you would have 2 times 2 10 times. That would be 2 to the 10th power, or 1,024 different options that you would have to write out. Now, can you imagine writing out that sample space by hand? That would be ridiculous. And each one of those options would be 10 boy-girl mixes. So the first would be boy, 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 boy. That is a single it's a single outcome in the sample space. So that's pretty intense. Go on and give this one a shot. So the number of blood type, sign, and chromosome matches. So you'll have 4 options for blood type, 2 options for sign, and 2 options for chromosome. Find out how many total ways that we can mix these up there are. Pause the video and give that one a shot. So looking through here, we've got 4 options, 2 options, 2 options. Fundamental counting rule says we multiply these. 4 times 2 times 2. There are 16 total blood type, sign, and chromosome mixes that we can have. Pause the video and give the shot for calculating the total number of 5-digit zip codes. So each of the possible 5 digits has 10 total options. So K1 is going to be 10, K2 is going to be 10, K3 is going to be 10, and so on. So we could do 10 times 10 times 10. That would be 10,000 total possible options. So the size of the sample space, the size of the total number of 10-digit zip or 5-digit zip codes that occur is 10,000. This is definitely one that you can't draw out by hand, and this illustrates one of the other advantages of using counting rules as opposed to drawing out the sample space or the event space, is that we can actually approach problems that we physically couldn't even approach without using this strategy. Now for our last example, try finding the total number of license plates you can have, where the first 3 are numbers and the second 3 spaces are letters. Pause the video and give this one a shot. Now this is definitely one that you can't do by hand. So we've got 3 with 10 possibilities each and 3 with 26 possibilities each, the letters A through Z. So 10 times 10 times 10 times 26 times 26 times 26 gives 17.5 million different license plate possibilities. Crazy. Alright, so the fundamental counting rule is a way to identify the size of the sample space given the different components of a probability experiment. The factorial rule is our first approach in the number of ways that items can be arranged. Factorial is denoted in with an exclamation point after it, and it's spoken as in factorial. And again, the meaning is how many ways can n items be arranged. Now we calculate n factorial by multiplying n times n minus 1 times n minus 2 and so on and so on and so on down till we get to 3 times 2 times 1. So we just keep multiplying n times 1 less than n and so on and so on. So 5 factorial would be 5 times 4 times 3 times 2 times 1. By definition, we'll assume that 0 factorial is equal to 1. It really has to do with something called a gamma distribution. We will not go into this. Unless you want to, you can shoot me an email and we can talk about it if you really want to. But yes, 0 factorial is 1. 1 factorial is 1. And for this class's purposes, we'll just assume that's by definition. All right, so for examples, runners. 5 runners are competing in a race, and how many different arrangements can they finish? So again, factorial is the number of different ways that you can sort in elements. So we've got 5 elements or people, runners, that we want to sort. 1, 2, 3, 4, 5, first, second, third, fourth, fifth. How many different ways or arrangements can we do that with for these 5 people? This is clearly a factorial problem. So we do 5 factorial, that's 5 times 5 minus 1, 4, and we do that all the way down till we get to 3 times 2 times 1. That gives us 120 different ways in which we can arrange those 5 runners. Now consider the intuition behind this. In the 5 runner problem, if we look at the first place slot, so actually I would think of drawing 5 little lines, line, 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 line. So we've got 5 spaces to fill. Now in the first space, when we're thinking about runners in a race, think about all these people are out running on the field, run, 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 run. The first space, there are 5 different people who could fall into this as they're running. But as soon as the first person crosses the finish line, well, we've got that first space locked in. The second space only has 4 people still left out running their race. And then as soon as somebody crosses the finish line for the fourth, or for the second place, the third space only has 3 people still out running, and so on and so on. So the intuition as to why we keep dropping one when we multiply all these together can be seen through that, if you will. Tree diagrams can still be helpful to make sure that we're not missing possibilities and can go through, okay, well, if person A took first place, what are the different options for person B, and so on. Now consider if we had 5 runners, but we only care about the top 3 finishers, we could look at the different arrangements for the top 3 finishers. Now we still have those 5 spaces, but I only care about the first 3 spaces now instead of all 5. So if I think about those blanks as we just explained them, I've got 5 possibilities for the first blank, and then once that person comes in, I've got 4 possibilities for the second blank, and then once that person comes in, I've got 3 possibilities for the third blank, and then I just ignore the last 2 because I'm only interested in the top 3 finishers. So if I've got 5 runners and I'm looking for the number of arrangements that I can make for the top 3 finishers, that number is going to be 5 times 4 times 3, or 60. This type of calculation is called a permutation. And if we're looking for the number of arrangements of different objects in a specific order using not all of the objects, so like in the last example we had excuse me, the number of arrangements of 5 runners, but we didn't want to look at all of the runners, we just wanted to look at the top 3 positions. So this is the permutations where we just want to look at the top however many. In this case we denote that letter as R, and we use n to describe, in the previous example, how many total runners we have. It's called a permutation. Now note with permutations, and this doesn't mean a lot right now, but it will in a bit, that order matters in permutations. That is, it matters who comes in first place, who comes in second place, who comes in third place, as opposed to if it really didn't matter, just as long as the 3 people cross the finish line. We'll talk about some examples in a bit. How we calculate permutations is we take n factorial and divide by n minus r factorial. Now note that these parentheses cannot be ignored. You have to do n minus r before you take the factorial, and it's a common mistake by students to try to do n factorial minus r factorial. Note that there's parentheses around here. This is n minus r. Do that subtraction problem first, and then find the factorial. That's super important. Note that order matters here. So this is again saying that person A, person B, person C, if A comes in first place, B comes in second place, C comes in third place, that is different than if C comes in first place, B comes in second place, and A comes in third place. So it matters who comes in first place is what this is talking about. All right, for example, the runners. Last time we talked about this, but now we'll use the formula. So last time we said we have 5 runners. We're looking at the top 3 places, and we actually calculated that out using our intuition. Now we'll use the formula, though. Have 5 runners. Want to look at the number of arrangements for 3 at a time. And again, in a race, the order in which you come in matters. It matters if you get first place versus second place. There's a difference. So the total number of objects that we're sorting is 5. We're sorting 5 people. Those are the 5 runners. And we're only sorting 3 of them. That is, we only care about the first 3 places. We're not sorting all 5 of them. So this is our permutations formula. Again, I just used the equation that was shown on the previous slide, and I substitute in the r value and the n value in the appropriate locations. Recall that I do the 5 minus 3 very first thing, so I'm left with 5 times 4 times 3 times 2 times 1 divided by 2 times 1. This is 5 factorial divided by 2 factorial. Now what you'll notice in every permutations problem is some of the top is going to cancel with some of the bottom. So the 2 times 1 cancels with the 2 times 1 in the bottom cancels with the 2 times 1 in the top. And that just leaves me with 5 times 4 times 3 on the top, which is what we came up with earlier. So let's say a professor is running to class and dropped their notes, 19 pages of notes for this day, though they only need 4 pages. So it's like they dropped all of chapter 4's probability notes, but for today's class we only need the first 4 pages. After picking up the notes, how many possible arrangements could the first 4 pages be in? So we've got 19 total notes that were dropped, but we only care about the first 4 of them, and we're asking how many different ways could the first 4 of them be. It could be page 1, 2, 3, 4. That would be the correct order, but it could also be page 19, then page 14, then page 1, then page 8. So how many different ways could this happen? We use the permutations equation because the order matters. If I have page 1, then 2, then 3, then 4, that's very different than if I have page 4, then 3, then 2, then 1. If I'm teaching, if I taught page 4 first and then went to page 3, then the page 2, then page 1, nobody would understand anything that I'm talking about. So because order matters, we're using a permutation, 19p4. Then I sub in my n, 19, that's the total number of items I can select from, and 4, the total number of items, or pages in this case, I'm selecting. Recall, I do this stuff in the parentheses, very first thing. So 19 factorial divided by 15 factorial. Note that there's going to be a lot of canceling. So if I write out 19 times 18 times 17 times 16 times 15 times 14, and so on and so on and so on, on the top, and then on the bottom I write 15 times 14 times 13 times 12 times 11, blah blah blah, what I'm going to notice is that everything from 15 on down is in both the top and the bottom, and I can cancel out everything from 15 on down. This leaves me with 19, 18, 17, and 16. 19 times 18 times 17 times 16 is 93,024. There are 93,000 different ways in which those first 4 pages can be picked up if order matters. Now, one interesting question. This is the sample space. Let's say, what is the probability that they are picked up in the correct order? Well, this is the total number of possible ways in which they could be picked up. So this is the size of the sample space. But what's the probability they get picked up in the correct order? So the event is they're in the correct order. How many total ways can we pick them up in the correct order? That is, how many total outcomes are in our event space? Well, there's only one way to pick the first 4 pages up in the correct order, and that's to pick them up in the order 1, 2, 3, 4. Any other order would not be the correct order, so there's only one. That means that when we look at the number of successes, or the size of our event space divided by the size of our sample space, we have 1 divided by 93,000. There's a 1 in 93,000 chance that if I dropped 19 notes on the floor and they were randomly scattered about, that the first 4 pages I picked up would actually be in the correct order. Pretty unlikely. Now, what if we wanted to deal with the same situation, but we didn't care about the order? Now, it's kind of hard to imagine this situation, but let's walk through it. Let's say I was going to select 5 students from our class to go to a pizza party. Now, it doesn't matter if you're the first person selected or the last person selected, you still get to go to the pizza party. So that's a great example of when order doesn't particularly matter. Versus if I'm going to give the first place student $100 and the second place student $50 and the third place student $25, you'd really want to be the first student selected. This idea of a pizza party, it doesn't really matter if you're first or third, you all get the same reward. So in the case that it doesn't really matter what order the objects go in, then we have a slightly different equation and a slightly different word for that. Recall that when order matters, we called that a permutation. When order doesn't matter, we call it a combination, and it's going to have a very similar but slightly different equation. The combination is denoted in CR instead of in PR. And in the combination, we still have n factorial divided by n minus r factorial, and we still have to do the stuff in parentheses first. However, in the combination, there's an additional element, r factorial, on the bottom. Now let me give you a big warning. Write this down for when you're practicing on your homework. You do the n minus r first, and you get whatever that number is factorial. Then you solve the factorial first for both this n minus r factorial and r factorial, and then you multiply them together. Okay, so you take these in the proper order, that is, do your parentheses first, then do the first factorial and the second factorial, and then you multiply those together. Again, order doesn't matter. So actually what we're ending up doing here is we're taking the permutations equation where order matters, and we're dividing out the total number of ways that you could arrange those R values that you have. That's all that this combinations formula is doing. So for example, a journal received 10 articles to publish but only has room for 3 articles. Now it doesn't matter if your article is first or second or third in the journal. If you get published, you get published. So all you have to do is be selected, and order doesn't matter. Given that order doesn't matter, how many different ways can you select the articles for inclusion? Well, because order doesn't matter, we're going to use a combination equation. So for the combination, I have to determine how many articles do I have to select from, and how many articles am I actually selecting. I have 10 articles to select from. I have 3 articles that I'm actually selecting, so my combination is going to be 10 choose 3. 10 is my n, so it's going to be 10 factorial divided by 10 minus 3 factorial times 3 factorial. Now note how I do this is I wrap the first factorial in parentheses and the second factorial in parentheses, so I make sure that I do both of them first. So 10 minus 3 is 7, 7 factorial is 7 times 6 times 5, and so on and so on and so on. 3 factorial is 3 times 2 times 1. And then on the top I have 10 factorial written out. Now notice that I'm going to get some cancellation here. I'm going to have the 7 times 6 times 5 from the bottom cancel with the 7 times 6 times 5 from the top. Now some students get confused here because they don't write out both sets of factorials. They only write out one, they don't write out both. This is so important to realize that on the bottom there's two sets of 3 times 2 times 1. There's a set of 3 times 2 times 1 in this very first factorial, and there's a set of 3 times 2 times 1 in the second factorial. So only one of those is going to get to cancel out with the top. The second one is still going to be on the bottom. So we're going to end up with 10 times 9 times 8, what was left on the top, divided by 3 times 2 times 1, what was left on the bottom. Now you can reduce this if you want to cancel out the 9 with the 3, that leaves a 3 on the top, the 8 with the 2, that leaves a 4 on the top, but you certainly don't have to. The primary canceling that you have to do is to chop out the really, really big numbers so that your calculator can handle them. Actually, typically I put on an exam problems that are so big that your calculator can't handle it unless you do it with canceling. These cancelings can save you a lot of time, and they actually let you approach problems and do problems that your calculator physically cannot do. So let's do one of those examples just for fun. Sandy needs to select best friends. According to Twitter, Sandy needs 3 best friends, because if you've got too many, well, you just don't have time and money for any of them. And if there's too few, then you're lame because you don't have enough best friends. Sandy currently has 500 Twitter followers and wants to know how many ways can Sandy select the 3 best friends from their Twitter followers. Now thinking about this, Sandy is going to randomly select 3 best friends. It doesn't matter if you were selected first or second or last, you're in the best friends club. So this is a case where order does not matter. Now Sandy is selecting from 500 people, but Sandy's only selecting 3 people to be best friends with. So we've got 500, choose 3. This is a combinations problem because order doesn't matter. It doesn't matter if you're first or second or third. Plugging in our numbers, we get 500 factorial divided by 500 minus 3 factorial times 3 factorial. Now this is a case where if you try to type in 500 factorial into your calculator, it would just up and die. It would laugh at you. It would say, ha 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 ha, I'm not going to actually do that. That's ridiculous. However, there's a ton of canceling that can happen here. We've got 497, 496, 495, all the way down to 321. So we can cancel out for all of these numbers with what's on the top. So let's draw this out. I'm going to write out, and what I typically do when I'm writing this is I write out the top factorial until I get to the numbers that are going to start to cancel. So I know that I can start to cancel at 497 on the bottom, so I'm going to write out the top factorial until I get to some of those numbers that are going to start to cancel. So 500, 499, 498, 497, and then I note that everything from 497 all the way down to 2 times 1 is going to cancel with what's on the bottom. So my 497 all the way down cancels with 497 all the way down on the bottom, and that leaves me with 500 times 499 times 498 on the top, and just the 3 times 2 times 1 on the bottom. So ultimately, Sandy has 20,708,500 ways in which they can select their 3 best friends from 50 Twitter followers, given the fact that it doesn't really matter if so-and-so was selected first or second or third. There'd be even more ways if it did matter who was selected first or second or third. On your own, why don't you go on and pause the screen and see if you can determine how many different ways there are to select a board of 4 students from our 30 student class. All right, now when we're considering this problem, remember, order doesn't matter here. Why doesn't order matter? Well, it doesn't matter if you're the first person on the board or the last person on the board. You're still serving on the board of advisors for the statistics, the basic statistics 1 course. So we're using a combinations problem. There are 30 students to select from. We're only selecting 4 of the students. So we have 30 factorial divided by 30 minus 4 factorial times 4 factorial. After doing some canceling, what I'm left with in the numerator is 30 times 29 times 28 times 27. And what I'm left with in the denominator is 4 times 3 times 2 times 1. This gives me 27,405 different committees that we could have for the Basic Stats 1 course. And that's when order doesn't matter. That's when order doesn't matter. All right, some closing thoughts. Permutations are used when order matters. Classic examples are races. First and second place matter. Raffles. If you get first place, you get $500. If you get second place, you don't. You get less money. The order of pages. The order of like books in a book series or something like that. Any case where order matters, that's where we're thinking permutations. For combinations, we use combinations when order doesn't matter. A committee is a great example, and we talked about a couple of different cases. A poker hand's kind of an interesting one because it doesn't really matter if you got a card first or last. As long as it's in your poker hand, it's in your hand. So it doesn't really matter what order you got those cards in. Recall that factorial is the number of ways we can arrange things. Students tend to forget what factorial means. So what is in factorial? Well, in factorial is the number of ways that you can arrange in objects. So you could put the first object first, the second object second, and so on, or you could switch the first and second objects, or you can keep rearranging on and on and on. How many times can you do that and create unique arrangements? Well, you can do that in factorial times. And last but not least, combinations and permutations are very, very related. Combinations are just permutations where we took out the number of the organization, the fact that you care about the order in which the items were in. Combinations, we don't care, so we just divided out the order in which all of those items were in. Now this ends Chapter 4, our probability chapter. Don't forget to, as soon as you're done with this video, stop the video, go do your Chapter 4 journal right away before you forget. Give me 5 or 6 good sentences about what you learned, what you didn't learn, what you thought was interesting, what you didn't think was interesting, what was helpful, what you'd like to see improved in the future. In the next chapter, we'll talk about discrete probability distributions. We'll talk about constructing probability distributions for a random variable. This is going to be a little interesting and a little different than what we've been doing. We'll talk about finding the mean, variance, and standard deviation and expected value. Now, we've already talked about mean, variance, and standard deviation, and in fact, expected value is the mean, so we've already talked about that too, kind of. But now we'll talk about how do we find the mean of a variable. We talked about finding the mean of a data set. How do we find the mean of something that's random? How do we even begin to approach that? We'll talk about finding the exact probability of a certain number of successes in a binomial experiment, and then we'll also talk about finding the mean, variance, standard deviation, and expected value of a variable in a binomial experiment.